Alright, silly people, here's the situation. We're going to be looking back at a few Hamiltonians from Chapter 2 and figuring out, just classifying them based on if they have a discrete spectrum, or a continuous spectrum, or if they have bits of both, um, other than the ones specified in the problem statement, which are uh, the harmonic oscillator is an example of one that has only a discrete spectrum because you can only have certain energy values and certain eigen functions for the wave functions in the harmonic oscillator. But the same is also true for the infinite square well. So infinite square well, that corresponds to the potential of v of x equals, it's 0 inside the well, so 0 less than x less than a, where a is the length of the well, and then infinity otherwise. Only has certain eigenvalues for the energy, so those are e sub n equals n squared pi squared h bar squared over 2ma squared, where n are the positive natural numbers, I think. And then psi of n, the only allowed eigenstates of the system, are just the root 2 over a sine n pi over a x. Right. Now the delta function, or wait, no. I kind of spoiled it already, but whatever. A kind of Hamiltonian that only has a continuous spectrum, so there isn't any bound state or energy eigenvalue in here, is an interesting one. The free particle obviously has this property because it's just a particle floating through space. It isn't really defined by any potential, so yeah, it is going to only have a continuous thing. But before I do that part, I'm going to talk about the answer for part C, something that has both discrete and continuous eigenstates. Because if you remember, if you look back at the delta function well part of the problem, or part of the textbook, that is the potential that is v of x equals minus alpha delta of x. And on a graph, it kind of just looks like this, right? It says that there's only one energy eigenstate, only one bound state, corresponding to E equals minus m alpha over 2 h bar, right? Squared on the bottom there. So there's only one bound state with energy that, and the wave function for that is square root m alpha over h bar. And notice that the eigen energy there is negative, which is kind of interesting. So that means that the minimum potential here is actually minus infinity. So this negative energy is actually allowed to be here and have a normalizable wave function that corresponds to that, right? So that's kind of a rule as well. That this is problem 2.2. If you look, it's that if you have an energy value for a Hamiltonian, then that energy value must be greater or exceed the minimum value for the potential energy. So E is always greater than V min. Problem 2.2, if you want to look at that again. So given that rule, if we just flip the delta function well across the y-axis, so instead we have something like this. Now V min is 0, but we still have the same continuous states that we had before in the delta function well. but we lose the bound state because now this can't exist in our system anymore. So this is a only continuous thing, and this sort of potential here is called the delta function barrier. And it's talked about right at the end of the delta function well section of the textbook, in not very great detail, but it's just that. And then the equation, you can probably guess, is just positive alpha delta x is your only continuous Hamiltonian. All right.